Some of the opening salvos of the chapter have to do with organizing knowledge. And your author does a good job of asking silly questions sometimes that are illustrative of the topic. Does a Burmese, and I forgot the dog's name, but a certain dog have a liver? And this dog was apparently a charming and funny dog. And how to answer. Of course, any moving organism, any animal or mammal would have a liver. So how do we arrive at that? So here is that dog, by the way. Bernese mountain dogs. They look cute. But this idea of cognitive economy is one that we're implicitly striving for, even though we're not intending to. Properties and facts are stored at the highest level possible. So to recover information, you use inference, much as you did to answer this question about them having livers. Any animal or mammal is going to have some semblance of a liver. It's actually going to have a liver. A frog or a sperm whale will have a liver. So how do we arrive at that question? So among the ways in which this knowledge is presumably organized are in networks. And for about a 5 or 6 year period from the late 60s to the mid 70s, there were a few different authors that proposed networks that built on each other. And we finally arrived at the Collins and Loftus model in the mid 70s that tends to stand the test of time. But this Collins and Quillian model from 69, which I know that's 55 years ago, one of the older experiments, they tested the idea that semantic memory is analogous to a network of connected ideas. And as in later networks, connectionist networks, this one consists of nodes that correspond to words or concepts. And each node is connected to related nodes or pointers, etc. So these things tend to fire together and map together. So over the course of our lives, and this would have been ensconced at an early age, we learn about animals and buildings and cars and bicycles and anything that has properties. But a canary is yellow and it can sing. It's a subdivision of a bird, as is an ostrich that weighs 400 pounds and is very tall and cannot fly. And birds are subdivisions of animals, as are fish. And sharks and salmon are subdivisions of fish. So all of these assertions become ensconced. Now, one of the more obscure ones that your author uses too often, I think, is a mammal. I think your average citizen is not super up to speed on the difference between a mammal and an animal with respect to laying eggs versus live births and mammary glands, etc. But certainly birds and fish, being subdivisions of animals and all the properties that they have, are pretty well known by just about anybody. And we can answer questions fairly directly, as one of the graphs says. So I can answer the question about a canary. Can a canary sing, or is it yellow, or is it smallish, faster than is a canary a bird, or is a canary an animal? There's that economy. I can answer those things pretty fast. And there's an experiment that demonstrates that. Collins and Quillian tested the principle of cognitive economy. They reasoned that if semantic memory is analogous to a network of nodes and pointers, and if semantic memory honors the economy principle, then the closer a fact or property is stored to a node, the less time it should take to verify that. So I can verify that a canary is yellow faster than a canary is an animal. And their reaction time experiments demonstrated that. Now, by our standards, 55 years later, these experiments were kind of crudely rendered, but they were done on a computer. And the reaction time was about as accurate as it could have been for the time. It's kind of interesting. So Collins and Quillian's reasoning led to the following prediction. If a person's knowledge of these mountain dogs is organized along the lines of that figure that we just saw, they should be able to verify the sentence, a Bernese mountain dog has an exuberant disposition, which apparently it does, faster than it has live young, which of course any dog does. Note that the property has a good disposition is stored right with the node for Bernese mountain dogs. And here's that figure. They didn't have this available. It's a really awful scan. I apologize, but you can see it's right there. Has an exuberant disposition is far beneath it being a mammal. So my affirming that it's a mammal would be slower than it having an exuberant disposition. So it kind of makes sense. In their study, Collins and Quillian presented people with a number of similar sentences and found, as they predicted, that it took less time to respond to things that were close in the neighborhood, like a canary as a bird. And here's another poor capture. I'm going to owe you one. I feel terrible about this. But on the far left, it says, and it asks people to affirm this, a canary is a canary. And then on the next step up is a canary as a bird, and then a canary as an animal. It took slightly longer to affirm those things because they were farther up in that network. And the ones that were right next to it were affirmed more quickly. A fairly simple idea, but for its time, it was a strong suggestion that we have this sort of organization, if you will. And I'm sorry about the crudeness of that capture. It's pretty bad. So the model was called a hierarchical semantic network model of semantic memories because researchers thought the nodes were organized in hierarchies. Now, other researchers complemented this idea that things are stored in such a way that is semantic, things that are related to each other. So Meyer and Chenavant performed a few experiments, and it's a rather simple idea. This was something that my thesis capitalized on almost 34 years ago when I was a graduate student. They performed a series of experiments that elaborated the semantic network proposal. In other words, like concepts being stored together. They reasoned that if related words are stored close to each other and are connected in a semantic network, whenever one is activated, it'll spread to other ones. And this was revealed in a lexical decision task. So here's the task, and I've got it below on a table. The question is the word a real word? So bread and carpet are words, wrinkle is not. In some conditions that were within participants, a related word preceded the word, butter preceding bread, or butter preceding carpet. Butter and bread are related, butter and carpet are not. As it turns out, people were faster to correctly say that bread was a word, 770 milliseconds, or about 3/4 of a second, than they were to say that carpet is a word. Now, it's not a gigantic effect, 40 milliseconds, but nonetheless, it was real and pretty persistent. And then the final condition there, butter preceding the non-word didn't facilitate at all. So the suggestion is, if I encounter butter, it has the effect of stimulating the idea of bread, which I then confirm is a real word. And that's the idea of the semantic network. So the explanations went along the following lines. The word helps letter recognition because a node corresponding to a word is activated in the former case. This automatic activation facilitates recognition of all parts of the word. And Conrad argued that let me come back down a little bit further. Hierarchical models don't predict that so perfectly. A pig as an animal is confirmed faster than a pig as a mammal. I want to switch gears and get to that on the very next slide.